A lack of a grounded and grounding conductor is a serious safety hazard. Without a proper ground, the subpanel and connected equipment are not protected from electrical faults. This could lead to shocks, fires, or equipment damage. Sensitive sound equipment may experience humming and buzzing because the system is not properly grounded. Electrical noise from other equipment or external sources can interfere with the audio signals. The electrical code requires that all subpanels be grounded and bonded. The current setup is a code violation and must be corrected. The neutral conductor is not properly grounded. This means that the voltage between the subpanel and ground can fluctuate, causing electrical noise and potentially damaging equipment. A number 10 American wire gauge wire connected to the water pipe is insufficient as a grounding conductor. The grounding conductor must be at least the same size as the largest ungrounded conductor, which in this case may require a larger gauge wire. The water pipe may not be a suitable grounding electrode. The grounding electrode must be a cold water pipe or other approved location. The solution is to install a proper grounding system. Firstly, replace the number 10 American wire gauge wire with an appropriately sized grounding conductor, potentially a number 4 American wire gauge. Secondly, connect the grounding conductor to an approved grounding electrode. Thirdly, ensure that the subpanel is bonded to the grounding system. Proper grounding provides enhanced safety for personnel and equipment, reduces electrical noise and improves audio quality, and ensures compliance with electrical code requirements. In older buildings, electrical systems may not always meet current safety standards. One common problem involves subpanels that lack proper grounding and bonding. A subpanel is essentially a smaller electrical panel that receives power from the main electrical panel and distributes it to various circuits within a specific area. When a subpanel is not properly grounded, it creates a variety of safety hazards and operational problems. Firstly, it's important to understand the role of grounding in an electrical system. Grounding provides a safe path for electrical fault currents to return to the source, tripping a circuit breaker or fuse and preventing electrical shock or fire. A properly grounded system includes a grounded conductor, typically the neutral wire, and a grounding conductor, which is connected to a grounding electrode, such as a metal water pipe or ground rod. The grounded conductor is intentionally connected to ground at the service entrance, providing a stable reference point for voltage. The grounding conductor provides a low impedance path for fault currents. In the described scenario, the subpanel is fed with 3 hot conductors, likely 120/208 volts, without a grounded or grounding conductor. Instead, a number 10 American wire gauge wire is connected from the subpanel to a water pipe using a ground clamp acting as both the grounded and grounding conductor. This setup presents several problems. Firstly, the lack of a dedicated grounding conductor creates a significant safety hazard. If a fault occurs in the subpanel or connected equipment, a fault current may not have a lower impedance path back to the source. This can result in elevated voltage on metal parts, posing a shock hazard to anyone who comes into contact with them. The absence of a proper ground also increases the risk of fire. If a fault current cannot quickly return to the source, it can generate heat, potentially igniting nearby materials. Secondly, using a number 10 American wire gauge wire as both the grounded and grounding conductor is inadequate. The grounding conductor must be sized according to the size of the ungrounded conductors feeding the subpanel, as specified in the National Electrical Code, or NEC. In this case, since the subpanel is rated for 200 amps, the grounding conductor should be at least a number 4 American wire gauge copper wire, or the equivalent in aluminum. A number 10 American wire gauge wire is simply too small to safely carry the potential fault current. Thirdly, connecting the grounding conductor to a water pipe using a ground clamp may not provide a reliable grounding connection. While metal water pipes are often used as grounding electrodes, they must be properly connected to the grounding system using approved methods. A ground clamp may not provide a sufficient electrical connection, especially if the pipe is corroded or has non-conductive coatings. Furthermore, relying solely on a water pipe as the grounding electrode may not be sufficient. The NEC requires that the grounding electrode system include a supplemental electrode, such as a ground rod or ground ring, to ensure a reliable ground connection. Fourthly, the sensitive sound equipment connected to the sub-panel is experiencing humming and buzzing due to a lack of proper grounding. Electrical noise, which is unwanted electrical signals, can be introduced into the system through various sources, such as electromagnetic interference from nearby equipment or ground loops. A properly grounded system helps to minimize electrical noise by providing a low impedance path for these unwanted signals to return to the source. Without a proper ground, the electrical noise can interfere with the audio signals, resulting in humming and buzzing. Finally, the described setup is a violation of the NEC, which requires that all sub-panels be properly grounded and bonded. Bonding refers to the practice of connecting all metal parts of the electrical system, such as enclosures, conduit, and equipment grounding conductors, to create a continuous electrical path back to the source. This ensures that all metal parts are at the same potential, minimizing the risk of electrical shock. To correct these problems, the following steps should be taken. Firstly, install a dedicated grounding conductor from the main electrical panel to the sub-panel. The grounding conductor should be sized according to the size of the ungrounded conductors feeding the sub-panel, and it should be run in the same conduit or cable as the ungrounded conductors. Secondly, connect the grounding conductor to an approved grounding electrode system. This may involve installing a new ground rod or ground ring, or connecting to the existing water pipe and supplemental electrode. Ensure that all connections are made using approved methods and hardware. Thirdly, bond all metal parts of the sub-panel and connected equipment to the grounding system. This includes connecting the equipment grounding conductors from the branch circuits to the sub-panel's grounding bus and bonding the sub-panel enclosure to the grounding conductor. Fourthly, verify that the grounded conductor or neutral wire is properly connected to the grounding system at the service entrance. The neutral wire should only be connected to ground at one point, typically at the main electrical panel. Connecting the neutral wire to ground at multiple points can create ground loops, which can cause electrical noise and other problems. By implementing these measures, the electrical system will be brought up to code, and the safety and reliability of the sub-panel and connected equipment will be greatly improved. In addition to the previously mentioned points, it is crucial to further elaborate on several aspects to ensure a comprehensive understanding of the situation and the necessary corrective actions. Let's delve deeper into the specific problems and recommended solutions, providing more technical details and considerations. Firstly, let's address the issue of the missing grounded conductor, also known as the neutral conductor. In a 120/208 volt system, the neutral conductor is essential for providing a return path for current in 120 volt circuits. When there is no neutral conductor, the 120 volts loads may not function correctly or may experience voltage imbalances, leading to equipment malfunction or damage. To rectify this, a properly sized neutral conductor must be installed from the source panel to the sub-panel. The size of the neutral conductor should be based on the calculated neutral load, as per the NEC. In many cases, the neutral load will be less than the phase load, allowing for a smaller neutral conductor. However, it is crucial to perform the necessary calculations to ensure that the neutral conductor is adequately sized to carry the expected current. Secondly, let's discuss the importance of using the correct type of grounding electrode. While metal water pipes are commonly used as grounding electrodes, they may not always be the most effective or reliable option. Over time, water pipes can corrode or develop non-conductive coatings, which can impair their ability to provide a low impedance path to ground. In addition, some water utilities are now using non-metallic pipes, which cannot be used as grounding electrodes. For these reasons, it is often recommended to use a combination of grounding electrodes, such as a ground rod and a water pipe, to provide a more robust grounding system. Ground rods should be at least 8 feet long and driven into the ground until at least 8 feet of the rod is in contact with the soil. The NEC specifies the minimum distance between ground rods and other grounding electrodes, as well as the required resistance to ground. Thirdly, let's examine the role of bonding in the grounding system. Bonding is the process of connecting all metal parts of the electrical system together to create a continuous electrical path to ground. This includes bonding the metal enclosures of electrical equipment, metal conduit, and metal water pipes. Bonding helps to ensure that all metal parts are at the same potential, minimizing the risk of electrical shock. The NEC specifies the requirements for bonding, including the size of the bonding conductors and the methods of making connections. Bonding conductors should be sized according to the size of the circuit conductors, and they should be connected to the equipment grounding bus in the electrical panel. Fourthly, let's consider the impact of electrical noise on sensitive electronic equipment. Electrical noise can be generated by a variety of sources, such as electromagnetic interference from nearby equipment, ground loops, and harmonics. This noise can interfere with the operation of sensitive electronic equipment, such as audio equipment, video equipment, and computer equipment. To minimize the impact of electrical noise, it is important to use shielded cables, install filters, and provide a clean, isolated ground for the sensitive equipment. Shielded cables help to block electromagnetic interference, while filters help to remove unwanted noise from the power supply. An isolated ground provides a dedicated path to ground for the sensitive equipment, preventing noise from other sources from interfering with its operation. Finally, let's emphasize the importance of complying with the NEC. The NEC is a comprehensive set of standards for the safe installation of electrical wiring and equipment. Compliance with the NEC is essential for ensuring the safety of people and property. Electrical inspections are typically required to verify that electrical installations comply with the NEC. It is important to hire a qualified electrician to perform any electrical work and to obtain the necessary permits and inspections. By addressing these specific issues and implementing the recommended solutions, the electrical system can be brought up to code and the safety and reliability of the equipment can be greatly improved. Remember that electrical work can be dangerous, and it is always best to consult with a qualified electrician if you are not comfortable performing the work yourself. Always ensure that all electrical work is performed in accordance with the NEC and local electrical codes. Furthermore, understanding the practical implications of these concepts is crucial for effective troubleshooting and maintenance. Let's delve into more practical aspects of grounding and bonding in electrical systems. Firstly, consider the impact of improper grounding on the performance of sensitive electronic equipment. Electronic devices, especially audio and video equipment, are highly susceptible to electrical noise. Improper grounding can introduce noise into the system, leading to distorted audio, flickering video, and unreliable data transmission. In severe cases, it can even damage sensitive components. Secondly, the choice of grounding electrode is critical for ensuring a reliable ground connection. While metal water pipes are commonly used, they may not always be the best option, especially in areas with corrosive soil or where plastic pipes are used in the water distribution system. Ground rods, ground plates, and concrete encased electrodes are alternative grounding electrodes that may provide a more reliable ground connection. Thirdly, the size and material of the grounding and bonding conductors are important factors in determining their effectiveness. The NEC specifies the minimum size of grounding and bonding conductors based on the size of the circuit conductors. Using undersized conductors can limit their ability to carry fault current, increasing the risk of electrical shock and fire. Copper conductors are generally preferred over aluminum conductors due to their lower resistance and better corrosion resistance. Fourthly, the methods of making connections in the grounding and bonding system are crucial for ensuring a reliable electrical path. Loose or corroded connections can increase resistance, reducing the effectiveness of the grounding system. Approved connectors, such as compression connectors and exothermic welds, should be used to make connections. The connection should be clean, tight, and protected from corrosion. Fifthly, regular inspection and testing of the grounding system are essential for maintaining its effectiveness. Visual inspections can identify loose or corroded connections, damaged conductors, and other problems. Ground resistance testing can verify that the grounding system is providing a lower impedance path to ground. Sixthly, the concept of single-point grounding is important for minimizing ground loops and electrical noise. Ground loops occur when there are multiple paths to ground, creating a loop in the grounding system. This can introduce noise and interference into the system, especially in sensitive electronic equipment. Single-point grounding involves connecting all grounding conductors to a single point, eliminating the possibility of ground loops. Seventhly, the use of isolated ground receptacles is another technique for reducing electrical noise in sensitive electronic equipment. Isolated ground receptacles have a separate grounding conductor that is isolated from the building's normal grounding system. This provides a clean, noise-free ground for the equipment. Eighthly, the importance of surge protection in protecting electronic equipment from voltage surges and transients. Voltage surges can be caused by lightning strikes, power grid switching, and other events. Surge protection devices, or SPDs, can divert surge current to ground, protecting sensitive equipment from damage. Ninthly, the role of harmonics in electrical systems and their impact on grounding. Harmonics are non-sinusoidal currents and voltages that can be generated by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause overheating of conductors, transformers, and other equipment, and they can also interfere with the operation of sensitive electronic equipment. Proper grounding can help to mitigate the effects of harmonics. Finally, the importance of documentation and labeling of the grounding system. Accurate documentation of the grounding system, including the location of grounding electrodes, the size and rating of grounding conductors, and the methods of making connections, is essential for future maintenance and troubleshooting. Labeling of grounding conductors and equipment helps to ensure that the grounding system is properly maintained and modified. By considering these practical aspects of grounding and bonding, you can ensure that your electrical system is safe, reliable, and provides optimal performance for sensitive electronic equipment. Remember that electrical work can be dangerous, and it is always best to consult with a qualified electrician if you are not comfortable performing the work yourself. Furthermore, expanding on specific scenarios and practical examples can significantly enhance understanding. Let's consider several real-world scenarios to illustrate the importance of proper grounding and bonding. Firstly, imagine a scenario where a metal enclosure of an electrical panel is not properly grounded. If a fault occurs inside the panel, such as a wire coming loose and touching the enclosure will become energized. Anyone who touches the energized enclosure will be exposed to a potentially lethal electrical shock. Proper grounding of the enclosure provides a low impedance path for the fault current to flow back to the source, tripping the circuit breaker and energizing the enclosure, preventing the electrical shock. Secondly, consider a situation where a computer system is experiencing intermittent data errors and crashes. These problems could be caused by electrical noise in the grounding system. The noise can interfere with the sensitive electronic components in the computer, causing them to malfunction. Proper grounding, including the use of isolated ground receptacles and shielded cables, can reduce the noise and improve the reliability of the computer system. Thirdly, imagine a scenario where a lightning strike occurs near a building. The lightning surge can travel through the electrical system, damaging electronic equipment and even causing a fire. Surge protection devices, or SPDs, can divert the surge current to ground, protecting the equipment from damage. Proper grounding of the SPD is essential for it to function effectively. Fourthly, consider a situation where a variable frequency drive, or VFD, is causing harmonics in the electrical system. The harmonics can cause overheating of transformers and conductors, and they can also interfere with the operation of other equipment. Proper grounding, including the use of harmonic filters and shielded cables, can mitigate the effects of the harmonics. Fifthly, imagine a scenario where a hospital is experiencing problems with its medical equipment. The medical equipment is highly sensitive to electrical noise, and improper grounding can cause it to malfunction, potentially endangering patients. Proper grounding, including the use of isolated ground receptacles, shielded cables, and single-point grounding, is essential for ensuring the safe and reliable operation of the medical equipment. Sixthly, consider a situation where a manufacturing plant is experiencing frequent equipment failures. The equipment failures could be caused by voltage sags and swells in the electrical system. These voltage variations can be caused by improper grounding as well as other factors. Proper grounding, including the use of voltage regulators and uninterruptible power supplies, or opposites can mitigate the effects of voltage variations. Seventhly, imagine a scenario where a data center is experiencing problems with its network equipment. The network equipment is highly sensitive to electrical noise, and improper grounding can cause it to malfunction, disrupting network services. Proper grounding, including the use of isolated ground receptacles, shielded cables, and single-point grounding, is essential for ensuring the reliable operation of the network equipment. Eighthly, consider a situation where a broadcast studio is experiencing problems with its audio and video equipment. The audio and video equipment is highly sensitive to electrical noise, and improper grounding can cause it to malfunction, degrading the quality of the broadcast. Proper grounding, including the use of isolated ground receptacles, shielded cables, and single-point grounding, is essential for ensuring the high quality of the broadcast. Ninthly, imagine a scenario where a construction site is experiencing frequent electrical shocks. The electrical shocks could be caused by improper grounding of portable generators and electrical tools. Proper grounding, including the use of ground fault circuit interrupters, or GFCIs, and regular inspection of electrical equipment, is essential for preventing electrical shocks on construction sites. Finally, consider a situation where a home is experiencing frequent power outages. The power outages could be caused by improper grounding as well as other factors. Proper grounding, including the use of surge protection devices and backup generators, can mitigate the effects of power outages. These real-world scenarios highlight the importance of proper grounding and bonding in a wide range of applications. By understanding the principles of grounding and bonding, and by implementing proper grounding practices, you can ensure that your electrical system is safe, reliable, and provides optimal performance for all types of equipment. Remember that electrical work can be dangerous, and it is always best to consult with a qualified electrician if you are not comfortable performing the work yourself. Furthermore, it's important to understand the legal and regulatory aspects of electrical grounding and bonding. In most jurisdictions, electrical installations are subject to regulations and codes such as the National Electrical Code, or NEC, in the United States, which set minimum standards for safety. Failure to comply with these regulations can result in fines, penalties, and even legal liability. Electrical inspections are typically required to verify that electrical installations comply with the applicable codes. These inspections are performed by qualified electrical inspectors who are trained to identify potential hazards and ensure that the installation meets the minimum safety standards. It's crucial to obtain the necessary permits and inspections before performing any electrical work. This ensures that the work is performed safely and in compliance with the applicable regulations. Hiring a licensed electrician is also essential for ensuring that the work is performed correctly and safely. Licensed electricians have the training, experience, and knowledge necessary to perform electrical work in accordance with the applicable codes and standards. They are also insured and bonded, which provides protection in case of accidents or damages. It's also important to be aware of the potential legal liabilities associated with improper grounding and bonding. If someone is injured or property is damaged as a result of improper grounding, the responsible party may be held liable for damages. This can include the property owner, the contractor, or the electrician who performed the work. Adequate insurance coverage is essential for protecting against these potential liabilities. Finally, it's important to stay up to date on the latest changes to the electrical codes and regulations. The electrical codes are constantly evolving to reflect new technologies and safety practices. Staying informed about these changes is essential for ensuring that your electrical installations are safe and compliant. By understanding the legal and regulatory aspects of electrical grounding and bonding, you can protect yourself from potential liabilities and ensure that your electrical installations are safe and compliant with the applicable codes and regulations. Remember that electrical work can be dangerous, and it's always best to consult with a qualified electrician if you're not comfortable performing the work yourself.